Our today's topic is flip flops. Flip flops. Okay. The output of the digital circuits, like and or not, like that, are dependent entirely on the inputs. There was an input. Output depends upon the input. If the input changes state, output may also change the state. Okay. But sometimes there are requirements for a digital device that the output remain unchanged, even if the change in the input levels. This type of device could be used to store a binary number. Flip-flop is such a device to store a binary number. Okay. Flip-flop are used in the construction of registers, counters, and a number of other applications. In a sequential, I'll explain in the next video what we mean by sequential. Flip-flop serves as the key memory elements, and analysis of such circuits are done through the truth tables, characteristic equations of the flip-flop. Now today we are going RS flip-flop. Before going RS flip-flop, what we mean by bistable, any device or circuit that has two stable states is said to be bistable. Okay, example, a toggle switch is a bistable because it having the two stable states. Like this, a toggle switch, it may on or it may off. Okay, and on and off mean the two states. It is either up or either down depending upon the position of the switch. Right? This type of switch is also said to have the memory since it will remain as set until some changes its position. Likewise, a flip-flop is a bistable electronic circuit that has two stable states. That is, its output is either 0 or plus 5 volt DC. The flip-flop also has the memory since its output remains as set until it's done to change. Flip-flop or the switch can be regarded as the memory device. Any bistable device can be used to store one binary digit. When the flip-flop has its output set at 0 volt DC, then can be regarded as storing a logic 0. When its output is set as plus 5 volt DC, then storing a logic 1. This is, it is also called a latch. Now we are going to understand what's RS flip-flop. NOR gate outputs 0, 0, 1. 0, 1 is 0. 1, 0 is 0. 1, 1 is all zeros except 0, 0 is 1 only. Remember the NOR gate logics. So let's start with R and S. Both are 0, 0. Like R is here 0 and S is also 0. Now before discussing that was the output, we to remember, we to observe what was the previous state before discussing. Previous state, let we assume Q is 1 and Q bar is 0. Q bar is complement of Q. If Q is 1, Q bar will be 0. Let we assume that. So if the 0 is coming here, 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 and it will reach at here. Okay. And now 0 and 0, see the table. 0, 0 is 1. So here, the output of the NOR gate will give you the 1. The 1 is here Okay, so this one is coming, this one is flowing, and it is going, and reaches here. 1 0. See the table again. 1 0 is 0. So output of the NOR gate is 0. Now this 0, last state here it is important for the last state was Q1 and 0, and there is no change in the last state. It is as it is. When R is 0, S is 0, whatever the previous state, it will exist. Okay, so remember 0 0 last state exists whatever it is. Now we are going to see what happens if R is 0 and S is 1. So the previous state is 1 0. Q is 1 and Q complement is 0. Okay. Now this one is coming, one is coming, one is coming, one is coming, one here. See the table. 1 1 will give you 0. Okay. The 0 will be at here. And then this 0 will flow and will go and here. Now it is 0 0 is here. See the table. 0 0 is what? It is 1. So it will be 1 here. Okay, 1 means it is a set state. If Q is 1, it is called set. And remember, previous state was Q is 1 and Q bar is 0. And the result is coming the same. Now we think other way. If previous state was Q was 0 and Q bar was 1, then what will happen with 0 1? Okay. If the previous state was Q is 0 and Q bar is 1, then what will happen? Like the logic inputs are the same, 0 and 1. R is 1 and R is 0 and S is 1. But I altered the previous state. Okay, this is 0. This 0 is coming, and reaches here. 0 1. 0 1, what as output? 0. Okay, the 0 will come here. But Q complement, Q complement becomes now 0. So no 1 now. Q complement is 0 according to the NOR gate, this lower NOR gate. Now this 0, this will go, this will flow, is going, reaches here. No, what is 0 and 0? See the table. That 0 0 is 1. So 0 0 is 1. 1 is at here. 0 goes, no 0 now. Q is 1. Okay, Q becomes 1. Now the 1 is coming. 1 is, like coming. Is 1 1 is again 0. So Q complement is 0. So that's the result. So even whatever the last state, if R is 0, S is 1, it is 100% sure Q will always be 1. Whatever the previous state was, no problem. Q will always be 1. This is very, very important to remember. Okay, now let's coming for the next one. Now, next one we're thinking previous state as Q is 1 and Q complement is 0. And the two inputs R and S, that's 1, 0. If R is 1, S is 0, what will happen? Let's see. So R is 1. So this is R is 1 and S is 0. Okay, previous state remember 1 and 0. Okay, this one picking from it. Let this one is, this one is flowing, coming, 1, 0. 1, 0 what gives? 0. So output is 0, okay. This 0 is coming now, going to upper NOR gate, reaches here, 1, 0. What is 1, 0? 1, 0 is again unitable, it is 0. So it is 0. I am holding this 0 here and let that at Q it is 0 now. It's not 1 according to upper NOR gate. Okay, see, now this is 0. Now hold this 0 here and it will go, it coming here, and both inputs of lower NOR gate is 0, 0. So what is 0, 0? See the table, it is 1, the 1 comes here. Now it is okay. Q is 0 and Q complement is 1. This is right. So this is now 1, Q complement is 1, going, and this 1 reaches here, but no problem. 1, 1 is again 0. So this is a stable state. If R is 1, it is 100% sure whatever the previous state, but the Q will always be 0. If R is 1, Q will always be 0. That is called reset. Okay, that's no problem whatever the previous state exists. So it is called reset because Q is 0 and Q complement is 1. That's called reset. Okay. Now the previous state is what? Q is 0 and Q bar is 1. Now last one, 1, 1. If R is 1, S is 1, what will happen? Okay, the result will be forbidden. How it is forbidden? Let's see. R is 1, S is 1. Previous state is 0, 1. So let's hold the 1. This one is going, reaches here. Now what is 1, 1? That is 0. So okay. This Q is 0 is okay. Now hold this Q, this 0. Now this 0 will coming, 0. Now what is 0, 1? Again 0. See the table, 0, 1 is again 0. So this 0 will be at here. Q complement becomes 0. No, this is a problem. Okay, both Q and Q complement are 0. So this is a big problem. This 0 is going, reaches here. 1, 0 is again what? 1, 0 is again 0. Now Q is 0, Q complement is 0. This is not possible. It is forbidden because QR1 S1 is forbidden because it forces the output of both NOR gate to low state. Okay, this is not valid. So that's why we call it forbidden, because Q and Q complement both coming equals to 0. It is never, it should not happen. Okay, thank you. This is clocked SR flip-flops. This is the circuit of normal SR flip-flop. What we did, two AND gates are connected. One AND gate with one input of the SR flip-flop or RS flip-flop, and second AND gate is connected with the second input of RS flip-flop. Now the input comes here, like this is R, this is S. Previously the input was at here and at here. Now the inputs are at here and at here, R and S. And second input of AND gate is connected together, and that is called the clock. Now the property of the AND gate is it gives high only when here is high and here is high. If the clock is high, then whatever the position, whatever the input of R and S, those input will be transmitted. Okay, when the clock is high. If the clock is low, whatever here it is, it will give always here 0 and 0 if the clock is low. So let's see the truth table. Clock is low, cross mean it is low. What will happen? The here will be 0 and here will be 0. R is 0 and S is 0. Now 0, 0, what happen? There will be no change in the output state of this circuit. So no change means the previous position will hold. Now let it the clock becomes high. Now let it the clock becomes high. Like this is high, this is high, this is high. If the clock is high and if S is at this is 0, this is 1, what happen? That the Q, this position, the Q will be at the 0. If the Q is 0, that is the reset state. If the clock is high and S is 1 and R is 0, S1 mean if the clock is high, these two inputs will be transmitted. Okay, then S becomes high at here and R becomes 0 at here. Then what happen? The Q will be high. Here it will be high and it will be low. So it is Q is high. High mean set state. Okay. The last one is when the clock is high and here it is 1, here it is 1. 1 1 will be transmitted here and here. If 1 1 is here, 1 is here, that is forbidden state. We always avoid these states. Q should be complement to this. The Q and Q bar, they should be of complement of each other. So, but it never happens. It is not the case of 1 and 1. That's why it is called forbidden state. Okay. This is clocked S. Hello, today's topic is D flip-flop. It is actually the RS flip-flop, only the addition that at one of the input of the AND gate or NOT gate is attached. This is point R, this is point S. This is D, at D is given a 0 and 0 comes here, and because of the NOT gate, 0 convert, 0 to becomes 1 at point R. Let the enable is high. If the enable is high, look in the table of the RS flip-flop, clocked RS flip-flop. Like SS0, RS1, clock is high, and the output, like the Q becomes 0, 0 means reset state. So if the day is 0, that becomes the reset state. So D flip-flop is reset when D equals to 0. Okay. So D equals to 0 is the highlighting area. Highlighting area. So here clock is high, S is 0, R is 1, and Q equals to 0. This is the reset state. Now, again, R equals to this point R, this is point S. Now let's say they are D equals to 1, and 1 comes here, and because of the NOT gate, R becomes 0, and let the clock is high. Just look the table. This is S is 1. Clock is high. R is 0. So what happened? The Q becomes 1. That's the set state. So Q becomes 1 means the set state. D flip-flop becomes set when D is equals to 1. D1 means set state of the D flip-flop. Okay. So D equals to 1 means set, D equals to 0 means reset. So only 2 inputs can be given here and D flip-flop. So highlighting the area, like this area, like for D equals to 1. This happens for D equals to 1 now. Now remember that only the at R and S will be complement here because of the NOT gate attached at one of the input of the AND gate. So it's not possible here for giving 1, 1 both at R and S, or giving 0, 0 both at R and S. Okay, so that's why this state is deleted now. That's not possible because of the NOT gate attached at one of the input of the AND gate. Okay. Now let's think about like if the clock goes to low. If the clock is low, you know what happens? The output of the AND gates, they gives low, and when the output of the AND gate gives low, whatever the previous state, it will retain as it is. It will exist as it is when the clock is low, because output of the two AND gates, they becomes the zeros or the low level. When the output of the AND gate low, that means the previous state, and then the changes at D will not be transmitted at the output, okay, when the clock is low.